Rivers of energy, wider than galaxies, carve paths across the cosmos. These are relativistic jets, and we are going inside the galactic engines that launch them for hundreds of thousands of light years. By the end, you will understand the fundamental forces that literally shape our universe. How can a single object power such an immense structure? And what does their existence tell us about the nature of reality itself? What does it make you feel to know such powerful engines are constantly at work in the darkness? A single light year is a distance so vast it defies easy understanding. Light, the fastest thing we know, takes an entire year to cross it. Now multiply that single unit by hundreds of thousands. The resulting scale is one where galaxies themselves become mere waypoints. Picture a thread of raw power so long it could stitch together our own Milky Way and the Andromeda Galaxy, our nearest major neighbor. That immense span of over 2 million light-years would represent just a small segment of one of these cosmic jets. In truth, many stretch for distances that would require a chain of dozens of galaxies laid end to end. How do we even begin to measure something so colossally large? Astronomers piece together observations from across the electromagnetic spectrum, carefully mapping the faint glow that betrays the jet's presence against the profound blackness of intergalactic space. This is not just an academic exercise. The sheer physical size of these structures is our first and most vital clue. It tells us that the engine which launched them cannot be a fleeting event. It must be a sustained, unimaginably stable powerhouse, operating relentlessly for millions of years without faltering. To propel energy across such a gulf of space requires a source of power that dwarfs the combined light of every star in a galaxy. The existence of these jets forces a single, pressing question into our minds. What kind of cosmic furnace could possibly burn with such ferocious and focused intensity for so long? At the heart of this cosmic powerhouse lies the ultimate trap for reality itself, a supermassive black hole. These are not the voids of nothingness we sometimes imagine, but objects of such incredible mass that their gravity warps the very fabric of space and time around them. Think of our own sun, a colossal ball of fire that anchors our entire solar system. Now envision an object millions, even billions of times heavier. That is the scale of a typical supermassive black hole, and one resides quietly at the center of our own Milky Way galaxy, as they do in most large galaxies. This immense gravitational pull is the foundational force, the primary engine. It acts as a cosmic attractor, relentlessly drawing in the gas, dust, and even entire stars that wander too close. This material does not fall straight in. Instead, it forms a vast, swirling, superheated maelstrom called an accretion disk, a whirlpool of matter spiraling inward at nearly the speed of light. The energy generated here is staggering, outshining the galaxy itself, but the true boundary, the point that defines the black hole's absolute dominion, is the event horizon. This is not a physical surface you could touch, but a mathematical line in the cosmos, a threshold of no return. Once any object, even a single photon of light, crosses this invisible boundary, it is lost forever to the universe outside. Nothing, no force we know of, can pull it back. It is this dramatic edge, this ultimate point of separation, that sets the stage for the incredible violence that happens just outside it. The event horizon marks the border where the familiar laws of physics are stretched to their absolute limit, creating the extreme conditions necessary to launch jets across the universe. This swirling vortex of matter is the second engine in our cosmic power plant. the accretion disk is where the raw potential of gravity is forged into pure energy. As gas and dust are pulled inward by the black hole's immense gravity, they do not fall in a straight line. Instead, they begin to orbit, piling up into a flattened, frenzied whirlpool. Different layers of this disk rub against each other at phenomenal speeds, creating immense friction that heats the material to millions of degrees. It glows with the combined fury of billions of stars, a radiant signature we can detect from across the universe. This process of friction and compression is astonishingly efficient, converting the gravitational energy of the falling matter directly into the intense heat and radiation that makes the disk shine so brightly. But the structure of this disk is not uniform. Astronomers often distinguish between thin and thick accretion disks. A thin disk is a tightly wound, orderly structure where particles orbit in a relatively flat plane. A thick disk, by contrast, is more like a puffed-up, turbulent donut of superheated gas. The type of disk that forms has profound consequences. A thick, chaotic disk is often far more effective at generating the complex magnetic fields needed for the next critical step. As this entire disk spins, the charged particles within it create and twist magnetic field lines, wrapping them around the black hole like cosmic strands of spaghetti. These magnetic fields become tightly wound and incredibly powerful, storing vast amounts of energy. They are the crucial scaffolding that will eventually channel and launch the jets themselves. The Event Horizon Telescope's famous image of the black hole in Galaxy M87 provides our most direct evidence. That iconic orange ring of light is not the black hole itself, but the unimaginably bright glow of its accretion disk, a whirlpool of energy confirming our theories. This disk is the violent, brilliant transformer that takes the simple, crushing force of gravity and prepares it for its ultimate task, focusing that raw power into the magnetic beams that will stretch for hundreds of thousands of light years. These magnetic fields are the third and perhaps most crucial engine in the system. They transform the chaotic inferno of the accretion disk into a focused cosmic cannon. Picture the most powerful electromagnet you can conceive, then multiply its strength by a factor of billions, and you begin to approach the forces at play just outside the event horizon. The relentless spin of the disk, combined with the black hole's own rotation, acts like a cosmic dynamo. It grabs the magnetic field lines that are embedded in the superheated gas and stretches them, winds them, and twists them into impossibly tight coils. These lines are not mere abstractions, they are physical structures under immense tension, like rubber bands being wound up to their breaking point. This process creates a powerful, structured funnel that rises from the poles of the black hole, a magnetic barrel that can guide and accelerate matter to incredible speeds. One of the leading theories explaining how this works is known as the Blandford-Zienagic process. It proposes that a rotating black hole can actually transfer its own rotational energy outward, but it requires a conduit. The twisted magnetic fields act as that conduit, like a gigantic electrical wire tapping into the spin of the black hole itself. The energy is extracted from a region just outside the event horizon called the ergosphere, where space itself is dragged around the black hole. Researchers using supercomputer simulations have watched this process unfold, confirming that these magnetic processes are dominant in both collimating, which means keeping the jet tightly focused and powering it over its incredible journey. We see direct evidence for this in jets like the one from Galaxy M87. Observations show that the magnetic field lines are aligned perfectly along the jet's structure, running like guiding rails for over 5,000 light-years. This intricate dance of magnetism does more than just shape the jet. It sets the stage for the final, breathtaking act, accelerating ordinary particles to speeds so fast they defy common sense. This transformation from raw power to visible light hinges on a process of staggering violence. Deep within the magnetic funnel, individual particles like electrons and protons are caught in an invisible storm. They are whipped to velocities so extreme they approach the universal speed limit, the speed of light itself. This is a cosmic particle accelerator, but one that makes our most powerful machines on Earth seem like toys. The mechanisms that achieve this are as brutal as they are effective. One primary driver is magnetic reconnection. Picture two powerful magnetic fields stretched to their breaking point, suddenly snapping and reconnecting with each other. This explosive event releases a colossal wave of energy, flinging any nearby particles outward with unbelievable force, like a cosmic slingshot. Another key process involves shock waves. As the jet plows through the thin intergalactic medium or even encounters slower moving material within itself, it creates titanic sonic booms. These shocks act as immense barriers, and particles crossing them gain a tremendous burst of speed, much like a surfer being hurled forward by a crashing wave. Once these particles are accelerated, they must announce their presence to the universe, and they do so through light. The first method is synchrotron radiation. Imagine an electron spiraling at nearly the speed of light along a tightly wound magnetic field line. This frantic corkscrew path forces the electron to emit energy, and that energy emerges as a broad, steady glow we can detect, especially strongly in radio waves. This is the primary reason our radio telescopes can map the vast, faint structures of these jets. The second method is even more direct, known as inverse Compton scattering. Here, a hyperfast electron smashes into a low-energy photon like a particle of starlight. In the collision, the electron transfers a huge amount of its own energy to the photon, effectively kicking it up the energy ladder. That gentle photon is transformed into a powerful X-ray or even a gamma ray, the most energetic form of light in the universe. We can see these processes at work by studying different cosmic monsters. Look at a blazar, a galaxy whose jet is pointed almost directly at Earth. The light from its jet is amplified and wildly variable, telling us that the most extreme particle acceleration is happening in a very small, turbulent region near the black hole. In contrast, the jet from a quasar like the one in 3C273 shows bright knots of light scattered along its length. Each of those knots is a site of intense shock waves, where particles are being re-accelerated hundreds of thousands of light years from their origin. It makes you wonder how many of the high-energy particles constantly raining down on our planet began their journey in such a distant, unimaginable engine. This final step, the acceleration of matter into light, completes the journey. It turns the silent, invisible force of gravity into a brilliant beacon we can see from across the cosmos. That brilliant light we detect from across the cosmos would be impossible without a final, crucial act of cosmic engineering. To travel hundreds of thousands of light years, the raw energy from the black hole must be focused into an impossibly narrow beam, a process known as collimation. Think of the difference between a gentle spray from a hose and the powerful, piercing stream created by putting your thumb over the nozzle. The universe has its own version of that nozzle, using immense forces to squeeze a chaotic outflow into a pencil-thin jet. This is not a simple task. The initial eruption of energy and matter from the vicinity of the black hole is often wide and poorly defined, like a raging fire hose before anyone has taken hold. For it to become a coherent beam, it must be confined and guided. Two primary forces work in concert to achieve this feat. The first is the external pressure of the hot gas that permanently surrounds the galaxy's center. This gas acts like a cylindrical pipe, constantly squeezing the jet from the sides and preventing it from expanding outwards too quickly. The second, and arguably more important force, is the jet's own internal magnetic field. You can picture these magnetic field lines as a tightly wound bundle of strings running the length of the jet. Their immense tension creates a powerful inward pinch force, like an invisible hand constantly tightening its grip to keep the beam perfectly straight and narrow. Supercomputer simulations reveal this dramatic transformation happening remarkably close to the black hole, within just a few dozen times the distance of the event horizon. The jet is born focused, and that focus is continuously refined as it travels, preventing its incredible energy from simply dissipating into the emptiness of intergalactic space. We can even see smaller-scale versions of this process at work much closer to home. In the nurseries where new stars are born, we find objects known as Herbig-Haro objects. These are brilliant patches of light created when jets from infant stars slam into surrounding gas clouds. While these stellar jets are trillions of times less powerful, they exhibit the same remarkable collimation, proving that the fundamental physics of focusing energy beams is a universal process. The existence of a perfectly straight jet stretching across a galactic void is a testament to a delicate and powerful balance, a natural engineering so precise it can maintain its form for millions of years. This power output is almost beyond comprehension, equivalent to the combined light of billions of suns burning simultaneously. To launch and sustain a jet for millions of years requires a cosmic energy budget of staggering proportions, forcing us to ask where all this power originates. Astronomers measure this output as luminosity, the total energy a jet radiates every second, and the numbers are consistently mind-bending. To make sense of it, they compare it to a theoretical ceiling known as the Eddington limit. This is the maximum amount of radiation a black hole can emit from its accretion disk before the outward pressure of that radiation overwhelms the inward pull of gravity, effectively shutting off the fuel supply. It is a fundamental balance between fire and force, yet we observe many jets that blaze far brighter than this limit should allow. Their luminosity screams that accretion alone cannot be the whole story. Something else, an even more potent reservoir of energy, must be tapped. This paradox points directly to the black hole itself, not as a passive drain but as an active power plant. The solution lies in two profound energy sources working in concert. The first is the gravitational potential energy of the accretion disk, the raw power released as matter spirals inward. This process is remarkably efficient, converting a significant portion of a particle's mass directly into energy as it falls. The second source is far more exotic, involving the black hole's own rotation. According to Einstein's theory of general relativity, a spinning black hole does not simply sit in space. It drags the very fabric of spacetime around with it, an effect known as frame dragging. The region where this dragging becomes inescapable is the ergosphere, a warped zone of reality just outside the event horizon. Here, space itself is forced to move. It is within this churning arena that the magnetic fields, rooted in the accretion disk, can act like a gigantic brake. They latch onto this spinning spacetime and extract rotational energy directly from the black hole, a process that can be far more efficient than accretion alone. This is the cosmic equivalent of connecting a generator to a colossal flywheel. Recent studies of different galactic cores reveal that not all black holes are equally generous with their spin. The efficiency of this energy extraction depends critically on the black hole's rotation speed and the precise configuration of the magnetic fields that encircle it. A rapidly spinning black hole entangled with a powerful, orderly magnetic field becomes an unparalleled cosmic dynamo. It can launch jets that not only surpass the Eddington limit but do so for eons, their power drawn from the slow, relentless braking of the black hole's spin. This intricate partnership between gravity, rotation, and magnetism solves the energy budget puzzle. It explains how these engines can sustain such phenomenal outputs without consuming themselves. Contemplating this, one must wonder about the broader impact. What happens to a galaxy, or even a cluster of galaxies, when such a torrent of energy is released into its heart for hundreds of millions of years? The answer reshapes entire cosmic structures. The raw power of these jets does not just travel across space, it also warps our perception of time itself. When matter is accelerated to over 99% of the speed of light, it enters a domain ruled by Einstein's theory of relativity, where the normal rules of reality break down in fascinating ways. One of the most dramatic consequences is a phenomenon known as relativistic beaming. Imagine a spaceship moving toward you at nearly the speed of light, its headlights blazing. The light from those headlights would not just appear brighter, it would be concentrated and focused directly into your path, its waves compressed into a much more energetic state. This is exactly what happens with a jet pointed almost directly at Earth, an object we call a blazar. The intense radiation from the jet is boosted, or Doppler shifted, into much higher intensities. This is why a blazar can appear thousands of times brighter than an identical jet pointing in any other direction, a mere trick of perspective amplified by the absolute laws of physics. This also affects the light's color, shifting it toward the more energetic blue end of the spectrum, a telltale sign of an object racing toward us. The opposite is true for a jet moving away, its light stretched and dimmed into red, often making it too faint for us to easily detect. This relativistic headlight effect is why our catalogs of these extreme objects are so heavily biased. We are naturally seeing the ones that are screaming directly at us. But the strangeness does not stop with light. Time itself flows differently aboard that hyper-fast jet. A clock within the jet would tick far more slowly compared to a clock in a distant control room, an effect called time dilation. For us as distant observers, this means any flicker or flare that happens in the jet's core appears to unfold in slow motion. A flare that might intrinsically last only a few hours could be stretched out over days or weeks from our perspective, its rapid variations smoothed and slowed by the incredible velocity of its source. This creates another layer of illusion, one that seems to defy the very speed limit of the universe, apparent superluminal motion. In some jets, we observe bright knots that appear to move across the sky faster than the speed of light. This is a cosmic mirage. The knot is not truly breaking any universal laws. It is simply moving almost as fast as the light it emits, and on a path very close to our line of sight. The knot is nearly keeping pace with its own light, so the later light it emits has a much shorter distance to travel to reach us than the earlier light did. This tricks our instruments into calculating a speed that seems impossibly high. We can witness this in action with blazars like Mysturk 421, which exhibits dramatic flares and knots that seem to move at several times the speed of light. These are not errors in our data, they are direct confirmations that the material in the jet is moving at a significant fraction of light speed. Every observation of a flickering blazar is thus a double message, telling us both about the violent processes happening near the black hole and about the fundamental, mind-bending nature of space and time. It forces us to ask how much of what we see is real structure and how much is a phantom cast by relativity itself. These cosmic engines are not isolated monsters, they are integral parts of their galactic homes, acting as both destroyers and creators. The energy they blast into space does not simply vanish. It slams into the vast reservoirs of thin, superheated gas that envelop galaxies, a process astronomers call feedback. This feedback is a fundamental regulatory mechanism, a cosmic gardener that prunes and nurtures the galaxy, controlling its growth and ultimate fate. The most dramatic effect is the quenching of star formation. For new stars to be born, giant clouds of gas must cool down, allowing gravity to pull them together into dense, collapsing knots. But when a jet plows through this galactic gas, it acts like a colossal blowtorch. The jet's energy violently heats the gas, preventing it from cooling. Without cool gas, star formation grinds to a halt. This is negative feedback, a powerful shut-off valve that prevents the galaxy from using up all its fuel too quickly and growing impossibly large. In truly massive galaxies, this is the primary reason we see so few new stars being born. The galactic engine has effectively put its own nursery on ice. We can see this process in action in famous galaxy clusters like the Perseus cluster. There, the jets from the central galaxy have carved out immense cavities, vast bubbles in the multimillion-degree cluster gas. These bubbles are direct evidence of the jet's energy input, pushing the gas aside and heating it from within, preventing it from cooling and falling back into the galaxy to form new suns. Yet the story is not solely one of suppression. The same violent process can, paradoxically, trigger creation. This is positive feedback. When the outward expanding shockwave from a jet crashes into a particularly dense and cold cloud of gas, the compression can be so intense that it overwhelms the heating effect. The cloud is squeezed, triggering gravitational collapse and a burst of new star formation right along the jet's turbulent edges. It is a cosmic paradox where the very force that prevents star formation in one area can ignite it in another. Cosmological simulations, the virtual universes run on supercomputers, now rely on this jet feedback to accurately model how galaxies evolve. Without including this energetic input, the simulations produce galaxies that are far too massive and full of stars, an issue known as the overcooling problem. The jets solve this by providing the necessary heating to regulate growth. This intricate dance of energy shapes the entire life cycle of a galaxy. It determines how many stars it will form, how bright it will shine, and even the types of planetary systems that might arise within it. The supermassive black hole at the center, through its powerful jets, becomes a master architect. This leads to a profound reflection. Our own Milky Way has a quiet supermassive black hole today. But what if it had been more active in the distant past? The very structure of our galaxy, the distribution of its stars and gas, may have been sculpted by ancient jets whose light faded eons ago. The legacy of these galactic engines is written not just in the void, but in the starry makeup of the galaxies they call home. The first clues arrived not as brilliant images, but as static hisses and crackles. In the 1950s, radio astronomers were mapping the sky with strange new instruments, discovering point-like sources of radio waves they called radio stars. One of the most powerful, Cygnus A, presented a profound mystery. It was incredibly bright, yet no visible star corresponded to its location. When astronomers finally pinpointed its origin, they found not a star, but a distant, distorted galaxy. This was the first hint that some galaxies harbored engines of unimaginable power, capable of flooding the universe with radio noise. The theoretical challenge was immense. How could a single galaxy produce more radio emission than the combined light of its billions of stars? Geoffrey Burbidge, among other visionary astronomers, grappled with this, proposing that the energy must originate from gravitational collapse on an unprecedented scale. They were laying the groundwork, suggesting that the cores of galaxies were sites of cosmic violence far beyond anything previously conceived. The true revolution, however, came with the identification of quasars. These objects appeared star-like, but their light revealed they were billions of light-years away. shining with the luminosity of 1,000 galaxies from a region smaller than our solar system. The only conceivable power source was a supermassive black hole, and soon observations revealed that many quasars were accompanied by faint, linear extensions, the first resolved views of the jets themselves. Linking these jets to active galactic nuclei was a monumental leap. It was the work of theorists like Roger Blandford, who began to mathematically model how a black hole's spin and surrounding magnetic fields could funnel energy into such narrow beams. The technology evolved in tandem. Single-dish radio telescopes saw only blurry points of light. The advent of interferometry, which combines signals from multiple telescopes to create a virtual instrument as large as the distance between them, finally gave astronomers the resolution needed. They could now see the intricate structures, the twin jets shooting out from a galactic core, confirming the theoretical predictions. This entire era was defined by a cycle of discovery. A new observational tool would reveal a strange new object like a quasar, forcing theorists to devise a new explanation, which in turn predicted what the next more powerful telescope should find. The story of these galactic engines is a testament to this iterative process, a slow and deliberate unraveling of cosmic mystery through human curiosity and ingenuity. It makes you appreciate that every detailed simulation we see today rests on decades of patient work, of scientists listening to the faint whispers of radio static and daring to imagine the roaring engines they represented. That global network of telescopes is now a reality, stitching together observations from across our planet to peer directly into the violent neighborhood of a supermassive black hole. The Event Horizon Telescope achieved the seemingly impossible, creating an Earth-sized virtual observatory to capture the first direct image of a black hole's shadow in galaxy M87. This was not a single photograph but a symphony of data, with radio telescopes from the South Pole to Hawaii and Europe recording perfectly synchronized observations. The resulting image, that now famous fiery ring, provided stunning confirmation of the intense light from the accretion disk and the dark shadow of the event horizon at its center. As one project scientist noted, this was like reading the fine print on a coin in Los Angeles while standing in New York City, a feat of engineering that pushed the boundaries of what we thought was possible. This very long, baseline interferometry allows us to see the very launch point of the M87 jet, linking the chaotic environment of the accretion disk directly to the base of that immense cosmic beam. But no single telescope can tell the whole story. The Chandra X-ray Observatory maps the incredibly hot gas shocked by the jet's passage, revealing cavities and ripples in the intergalactic medium. The Hubble Space Telescope captures the detailed structure of the jet itself in visible light, showing its knots and twists. Meanwhile, gamma-ray telescopes like the Fermi satellite detect the most energetic particles screaming along the magnetic highways. By combining these views, astronomers create a multi-wavelength portrait of a jet's entire life cycle, from its violent birth to its impact on the cosmic landscape. A recent study of a distant quasar jet showcased this power, with radio data outlining the magnetic field structure, X-rays pinpointing sites of intense particle acceleration, and gamma rays revealing the most extreme collisions happening within. These observations are constantly testing and refining our theoretical models, sometimes confirming predictions and other times presenting us with entirely new puzzles. What new secrets will we uncover as the next generation of telescopes, like the James Webb Space Telescope and even larger radio arrays, turn their gaze toward these cosmic engines? The heart of darkness is beginning to give up its secrets, one wavelength of light at a time. These digital universes are born from lines of computer code, translating the raw mathematics of Einstein's theories into a dynamic, visual reality. Inside a supercomputer, the chaotic environment around a black hole is not just calculated, it is brought to life. Researchers use a powerful combination of numerical relativity, which simulates the warping of space-time, and magnetohydrodynamics, which models the behavior of magnetized fluids, to recreate the entire jet launching process. This is not a simple animation, it is a full physics experiment running inside a machine, where virtual particles of gas follow the same laws that govern the real cosmos. The challenge is immense, for the simulation must seamlessly blend the bizarre rules of general relativity near the event horizon with the complex turbulence of plasma physics in the accretion disk, all while tracking how energy radiates away. Only then can the virtual engine produce a jet that matches what our telescopes see. Projects like the Black Hole Accretion Disk Code have done exactly this. Their simulations show a black hole's intense gravity pulling in matter, which then swirls into a hot, thick disk. The rotation twists magnetic fields into a tight bundle, and from the poles, a powerful, collimated jet erupts just as the theories predicted. These digital jets even exhibit the same knots and variations in power that we observe in real objects like blazars, offering a possible explanation for their dramatic flares. Watching these simulations unfold, one can see the invisible forces at work, the magnetic fields acting as a rigid skeleton that guides and focuses the outflow into a beam that punches its way out of the galaxy. How do we know these virtual worlds are accurate? The ultimate test is a direct comparison with nature. Scientists rigorously validate their models by checking if the simulated jet matches the observed properties of a real one, from its luminosity and spectrum to its detailed structure in radio telescope images. When the digital jet and the real jet align, it gives us tremendous confidence that we are understanding the underlying physics correctly. This process turns the supercomputer into a laboratory for testing ideas that are otherwise impossible to probe. It allows us to run experiments we could never perform in reality, like changing the black hole's spin rate or altering the magnetic field strength to see how the jet responds. These virtual experiments bridge the vast gap between abstract theory and tangible observation, letting us witness the birth of a cosmic jet from a perspective no telescope can ever provide. The principles that govern these titans are not confined to distant galaxies. We find the same cosmic recipe at work in our own cosmic backyard, operating on a far more intimate scale. Within the Milky Way, stellar mass black holes and neutron stars, the dense remnants of exploded stars, can also generate powerful jets. These systems are known as microquasars, and they act as perfect miniature laboratories. The fundamental physics is identical. A compact object provides the gravity, an accretion disk forms from a companion star's stolen gas, and magnetic fields channel the energy into narrow beams. Primary difference is one of sheer magnitude. A microquasar might be powered by an object only 10 times the Sun's mass, while a quasar's central black hole can weigh billions of solar masses. This scale difference reveals itself in the jets. The microquasar SS433, for instance, boasts jets that stretch for a fraction of a light year, a tiny structure compared to the 100,000 light-year beams of a quasar like 3C273. Yet proportionally, they are just as impressive. The energy output, while absolutely smaller, is generated with a similar ferocious efficiency. This scalability is a powerful testament to the universality of the physical laws at play. The same equations of gravity and magnetism describe the engine, whether it is a supermassive giant or a stellar weight counterpart. The key advantage of microquasars is their speed. Their smaller size means changes happen quickly. A quasar's jet might take centuries to show significant variation, but a microquasar can flare, flicker, and evolve over days, weeks, or months. This rapid variability allows astronomers to observe the entire life cycle of jet activity, from ignition to fading, within a single human lifetime. Watching a microquasar like GRS 1915+105 erupt provides a fast-forwarded view of the processes we believe occur near supermassive black holes. Experts note that by studying how these smaller jets remain collimated and transport energy, we can refine our models for their colossal cousins. The intense, rapid flares in a microquasar test our ideas about shock acceleration and magnetic reconnection under extreme conditions. This comparative approach reveals a profound unity across the cosmos. From the brightest quasars at the edge of the observable universe to the faint, flickering systems within our own galaxy, the same engine roars to life, scaled to fit its environment. It demonstrates that the universe has a preferred method for focusing raw power, a recurring pattern written into the fabric of space-time itself. Think of a black hole's spin as a colossal, hidden battery. This rotation, known as its angular momentum, is not just a simple twist, it is a reservoir of truly immense energy. The faster a black hole spins, the more energy is stored within the warped spacetime that is dragged around it. This spin is quantified by a number called the spin parameter, a value that tells us just how much of this rotational power is available to be tapped. It is this very spin that transforms a black hole from a passive consumer of matter into an active, efficient power plant for its jets. Two remarkable mechanisms allow this energy to be extracted. The first is the Penrose process, a theoretical concept where an object splits in two within the ergosphere, the region of twisted spacetime outside the event horizon. One fragment falls in, while the other escapes with more energy than the original object arrived with, effectively stealing rotational energy from the black hole. The second, and likely more dominant process in nature, is the Blandford-Zenagic mechanism. Here, the magnetic fields anchored in the accretion disk act like a gigantic brake, gripping the spinning spacetime and converting that rotational momentum directly into the focused power of the jet. How do we even measure the spin of an object that is, by its nature, invisible? Astronomers have developed clever techniques. One primary method involves studying the X-ray light from the innermost part of the accretion disk. The extreme gravity of a rapidly spinning black hole pulls this inner disk closer, altering the specific way the X-rays are emitted and creating a detectable signature in the spectrum. Another method is to correlate the measured power of a jet with theoretical models, allowing scientists to work backward and estimate the spin required to produce such a tremendous outflow. We see this connection clearly in active galaxies like NGC 1365. Observations from X-ray telescopes have shown that its central black hole is spinning at close to the maximum possible rate. This finding aligns perfectly with the observed powerful jet activity, providing strong evidence that high spin is a key ingredient for launching the most energetic outflows. It makes you wonder, how does a black hole acquire such rapid rotation in the first place? Is it born spinning, or does it gain momentum over billions of years by consistently consuming matter from a single direction? The evolution of a black hole's spin is a slow cosmic dance that ultimately dictates its ability to influence its entire galactic environment. Recognizing spin as a fundamental engine parameter completes our picture, revealing that it is not just the black hole's mass, but its rotation that truly unlocks the potential for these universe-spanning structures. The substance of these cosmic beams is a seething soup of fundamental particles, all racing at nearly the speed of light. While we often think of electrons and protons as the primary ingredients, the recipe is far more exotic, sometimes featuring positrons, the antimatter counterparts to electrons, and possibly even heavier atomic nuclei. This plasma composition is not merely a detail, it fundamentally shapes the jet's power, its stability over immense distances, and the very light it emits. To decipher this recipe from billions of light-years away, astronomers act as cosmic chemists, analyzing the radiation spectrum. Each type of particle leaves a unique fingerprint in the light. The smooth, broad glow of synchrotron radiation, for instance, tells us that ultra-fast electrons are spiraling along magnetic field lines. Meanwhile, the detection of extremely high-energy gamma rays can be a signature of proton collisions or other hadronic processes, suggesting the jet contains more than just lightweight particles. The polarization of this light, the specific direction its waves vibrate, provides another crucial clue, revealing the ordered structure of the magnetic fields that confine this particle soup. A major debate centers on whether most jets are dominated by lightweight electron-positron pairs or the much heavier electron-proton plasma. An electron-positron jet is like a cloud of identical twins, where particles and their antimatter mirrors annihilate upon contact, creating a very clean light flow. An electron-proton jet, by contrast, is far heavier, carrying immense momentum that can help it plow through intergalactic space without easily dispersing. The composition directly influences the jet's behavior. A lighter jet requires less energy to accelerate to fantastic speeds, but might be more prone to instability and disruption. A heavier jet is more stable and carries more raw power, but demands a far more powerful engine to launch it. We see evidence for this complexity in different cosmic objects. The relativistic jets from gamma-ray bursts, the most powerful explosions in the universe, often show signatures of a mixed composition, including heavy nuclei, which helps explain their incredible energy output and the afterglow we observe. In the more sustained jets from active galaxies, studies of their radiation and stability suggest many are likely light, electron-positron plasmas near their base, but may become heavier with protons and ions further out. This ongoing research is pushing into new frontiers. Scientists are now searching for neutrino emissions from these jets. Neutrinos, ghostly particles that barely interact with matter, would be a smoking gun, as they are almost exclusively produced by proton interactions. Detecting them would confirm the presence of a significant hadronic or heavy particle component. As one researcher noted, pinning down the exact mix of particles is like trying to determine the ingredients of a distant recipe by only studying the flickering light from its oven. This fundamental uncertainty about what the jets are truly made of reminds us that for all we have learned, the deepest layers of these cosmic engines remain shrouded in mystery, their full nature still emerging from the data. This silent, intergalactic emptiness is anything but empty. It is filled with a whisper-thin gas known as the intergalactic medium, and when a relativistic jet slams into it, the result is a cosmic battleground of staggering proportions. The jet acts like a titanic plow, pushing the gas aside and creating a colossal bow shock that races ahead of it. This shock wave is a wall of compressed energy, heating the gas to millions of degrees and causing it to glow brilliantly in X-ray light, a signature our space telescopes can easily detect. As this forward momentum continues, the jet's material itself balloons outward, inflating vast, buoyant bubbles known as radio lobes on either side of the galaxy. At the very leading edge of these lobes, we often find intensely bright regions called hotspots, where the jet's power is most violently concentrated and dissipated. The physics of this interaction are a complex dance of energy transfer. The jet does not simply stop. Its energy is converted into heat, radiation, and the kinetic motion of the displaced gas. Some of this material, unable to push forward, flows backward along the sides of the jet in a process called backflow, helping to inflate the lobes even further. This entire process acts as a powerful heating mechanism for the intergalactic medium, preventing it from cooling and collapsing under its own gravity. The consequences of this are profound, as it directly influences how large-scale structures form and evolve across the universe. We see this cosmic engineering in spectacular detail within galaxy clusters. The Perseus cluster, for instance, is a textbook example. Chandra X-ray observatory images reveal immense, dark cavities carved out of the cluster's superheated gas, perfectly aligned with the radio lobes emanating from the central galaxy. These are the jet-inflated bubbles, rising like cosmic hot air balloons through the cluster atmosphere. Their presence proves that the jet's energy is actively counteracting the natural tendency of the gas to cool and flow inward, a process that would otherwise lead to a catastrophic burst of star formation. This delicate balance between heating and cooling is a fundamental regulatory mechanism for the entire cluster's thermodynamics. It makes you wonder how many of the galaxy clusters we see today were shaped and stabilized by such ancient jets, their energy input echoing across billions of years. The interaction between these powerful beams and the fabric of space itself reveals that jets are not just spectacular phenomena, they are essential architects, quietly building and maintaining the cosmic structures we call home. These cosmic engines do not hum with a steady rhythm, they beat with a violent and erratic pulse. Their light can flicker and flare with breathtaking speed, transforming from a faint glimmer to a beacon thousands of times brighter in a matter of days. This variability is the engine's heartbeat, a direct signal from the chaotic core where matter and magnetism collide. The causes are as dramatic as the effects themselves. Sometimes a massive instability rips through the accretion disk like a seismic wave through a superheated ocean, sending a surge of fresh fuel toward the black hole. At other moments, the magnetic fields themselves snap. A magnetic reconnection event unleashes a storm of energy, like a cosmic circuit breaker overloading, flinging particles to insane speeds in an instant. Even changes in the black hole's feeding rate, a stellar snack versus a full-course galactic meal, can trigger a dramatic outburst that ripples down the entire length of the jet. To decode these rapid-fire messages, astronomers launch global campaigns, coordinating telescopes that see in radio waves, visible light, X-rays, and gamma rays all at once. This multi-wavelength monitoring is like having doctors with different specialties all examining the same patient simultaneously. A flare might begin with a burst of high-energy gamma rays from the jet's base, followed hours later by a surge in visible light, and then a slow rising tide of radio waves from further out. Each delay and each color of light tells a story about the sequence of events and the jet's internal structure. Nowhere is this volatility more extreme than in blazars like Lacerti. This object can change its brightness by a factor of hundreds in just a few hours. A flicker of such immense power, it challenges our very understanding of how particles are accelerated and cooled down so quickly. As one researcher noted, observing a blazar is like watching a storm in a teacup that is trillions of times more powerful than our sun and billions of light years away. These wild fluctuations are not just random noise, they are a rich diagnostic tool. The pattern and speed of the flares are intimately linked to fundamental engine parameters, like the black hole's spin and the strength of the magnetic fields near the event horizon. An extremely rapid flare suggests the turbulence is happening in a very small, incredibly violent region. The unpredictable, explosive nature of these jets is a constant reminder that we are witnessing a continuous state of controlled chaos. a turbulent environment where the fundamental forces of the universe are in a relentless and visible struggle for dominance. Even our most advanced simulations reveal a process that remains frustratingly incomplete. The precise sequence of events that ignites a jet, transforming a chaotic whirlpool of matter into a perfectly focused beam, is one of the greatest unsolved problems in astrophysics. We understand the ingredients, but the exact recipe eludes us. A central debate revolves around the primary power source. Is it the spin of the black hole itself, tapped through the twisting of space-time, or is it the furious rotation of the inner accretion disk that provides the crucial energy? Most researchers agree both contribute, but determining their relative importance in different cosmic monsters is a major challenge. This leads directly to the jet dichotomy mystery. Why do two galaxies, each with a similar supermassive black hole, sometimes produce dramatically different outcomes? One might launch a brilliant, universe-spanning jet, while its neighbor remains quiet and dark. The answer may lie in the history of the black hole's last meal or the innate stability of its magnetic fields, but we simply do not know for certain. Another profound puzzle is the origin of the magnetic fields themselves. Are these fields dragged in from the surrounding intergalactic gas, or are they generated from scratch by the turbulent dynamo of the accretion disk? The initial strength and configuration of these fields could be the deciding factor between a feeble outflow and a galactic-scale beam. These questions push our understanding of plasma physics into a realm of extreme gravity, where matter behaves in ways we cannot yet replicate in any laboratory. Competing models offer different pathways, each with its own predictions. The Blandford-Zenagic model champions the black hole's spin, while alternatives like the Blandford-Payne mechanism emphasize the power extracted from the accretion disk's rotation. Distinguishing between them requires looking for subtle signatures in the light from the jet's base, a task at the very limit of our observational capabilities. How can we ever be sure what these jets are truly made of, whether they are light electron winds or heavier proton rivers, when we cannot sample them directly? The light we receive is a tangled message, a composite of different processes. Resolving these mysteries will require more than just bigger telescopes. It demands new theoretical insights into the fundamental laws that govern matter under the most extreme conditions imaginable. What hidden principle of nature ensures that a structure hundreds of thousands of light years long does not simply fray and dissipate into the void? The enduring enigma of jet launching is a powerful reminder that for all we have learned, the cosmos still holds its deepest secrets close. The silent ripples in spacetime carry a message from the most violent collisions in the cosmos. Gravitational waves, first detected in 2015, are now opening a new window into the engines that power relativistic jets. This is the frontier of multi-messenger astronomy, where we no longer just see the universe but also feel its vibrations. The most compelling connection so far involves the merger of two neutron stars. When these incredibly dense stellar corpses spiral together, they can create a newborn black hole or a massive neutron star, surrounded by a swirling disk of leftover material. This is the perfect recipe for a jet. The merger event known as GW170817 was a landmark. The LIGO and Virgo observatories felt the space-time shudder, and seconds later, space telescopes detected a short gamma-ray burst, a telltale flash from a relativistic jet being launched. This single event confirmed that at least some of these brief, brilliant flashes are indeed the birth cries of jets from mergers. It provided a direct, multi-messenger view of a cosmic engine igniting. The challenge now is to find this signature for binary black hole mergers. Theorists suggest that under the right conditions, two black holes merging could also be surrounded by a dense cloud of gas and dust, potentially fueling a jet. Detecting such a jet, however, is incredibly difficult. The gravitational wave signal from black holes is clean and strong, but any accompanying light signature would be exceedingly faint, lost across the vast intergalactic distances that separate us from these cataclysms. Future observatories like the space-based gravitational wave detector LISA will be crucial. By listening to lower frequency ripples, it could pinpoint massive black hole mergers in the centers of galaxies much earlier, giving optical and radio telescopes the time and direction they need to hunt for the faint, emerging glow of a jet. As one researcher involved in the GW 170817 discovery noted, that event was our first glimpse of a complete story, from the initial collision to the resulting outflow. Each new multi-messenger detection is like adding another chapter, revealing how the chaotic aftermath of a merger can be forged into a perfectly focused beam of energy. This synergy between feeling the vibrations and seeing the light promises to answer fundamental questions. Does the spin of the final merged object dictate the jet's power? How quickly after the collision does the magnetic field coil itself into a launching structure? We are no longer just observers of these distant engines. We are beginning to witness their violent birth, and in doing so, uncovering the universal principles that turn cosmic chaos into a structured beam that can cross the universe. Some of the most energetic particles in the universe begin their lives within these magnetic storms. These are cosmic rays, atomic fragments racing through space at nearly the speed of light, carrying energies millions of times greater than anything produced in our most powerful particle colliders. Their origin was one of astrophysics' longest-standing mysteries, and the answer points directly back to the violent hearts of active galaxies. The sheer power of a relativistic jet makes it a perfect natural accelerator. Deep within its structure, shock waves act as immense barriers. When a proton or an atomic nucleus crosses one of these shocks, it gains a tremendous burst of energy, much like a ball being bounced repeatedly between two converging walls. With each crossing, the particle is hurled faster and faster, its energy growing until it reaches an almost inconceivable level. These ultra-high-energy cosmic rays are so powerful that their source must be phenomenally violent and capable of confining particles long enough for this acceleration process to work. A jet's immense length and strong magnetic fields provide the perfect, stretched-out racetrack for this purpose. The challenge has been tracing these ghostly particles back to their home. Cosmic rays are charged, so their paths are bent and scrambled by the magnetic fields they encounter during their journey across millions of light years. We cannot simply look back along a straight line to see where they came from. Instead, scientists have had to become cosmic detectives, looking for subtle statistical clues. Large observatories like the Pierre Auger Observatory in Argentina use a vast array of detectors to capture the rare air showers created when a single cosmic ray slams into our atmosphere. By studying the directions from which the very highest energy rays arrive, they have detected a faint anisotropy, a slight unevenness in their distribution that hints at an origin in nearby active galactic nuclei. But the most compelling evidence has arrived with a different messenger entirely: the neutrino. Neutrinos are ghostly particles that barely interact with matter, flying straight through planets and stars as if they were not there. This makes them notoriously difficult to detect, but it also means that when we catch one, it points directly back to its source, unswayed by magnetic fields. The Ice Cube Neutrino Observatory, a gigantic detector buried deep in the Antarctic ice, achieved a historic breakthrough when it detected a high-energy neutrino from a specific patch of sky. Astronomers immediately pointed every available telescope at that region, and found a blazing blazar known as TXS 0506 plus 056. The correlation was undeniable. A single ghostly particle had traveled for billions of years to deliver a message that this distant jet was a factory for accelerated protons. The implications ripple far beyond astrophysics. These high-energy particles constantly bombard our planet and have done so for its entire history. They contribute to the natural background radiation and may even play a subtle role in biological evolution by causing genetic mutations over geological timescales. Every so often, a particle with the energy of a well-thrown baseball arrives from the depths of space, its journey beginning near a supermassive black hole. It makes you wonder how many of the random changes in life's long history were triggered by a silent messenger from one of these cosmic engines. This heating system is a cosmic balancing act of astonishing precision. At the heart of a massive galaxy cluster, the intracluster medium glows fiercely in X-rays, radiating its thermal energy away into space. Left unchecked, this radiative cooling would cause the gas to cool, condense, and flow toward the cluster's center in a torrential downpour, fueling an unstoppable burst of new star formation. The entire central galaxy would swell into an overgrown monster of stellar light. Yet we do not see this. Instead, the gas maintains a stable, hot equilibrium, and the reason is the central black hole's jet. Like a perfectly tuned thermostat, the jet responds, pumping mechanical energy back into the gas and offsetting the cooling losses. This feedback loop ensures the cluster does not overheat or overcool, but maintains a steady thermal state for billions of years. We can witness this regulation in our own cosmic neighborhood. In the Virgo cluster, the giant elliptical galaxy Messier 87 serves as the central engine. X-ray observations from the Chandra telescope reveal a stunning landscape sculpted by its jets. Vast, dark cavities, each large enough to swallow thousands of solar systems, have been blown into the surrounding hot gas. These are the cosmic bubbles inflated by the jets, direct evidence of mechanical energy being deposited into the cluster atmosphere. Surrounding these cavities are subtle ripples, concentric rings of slightly denser gas that resemble sound waves propagating through the medium. These ripples are the echoes of past jet outbursts, each wave carrying energy that heats the gas as it dissipates. The entire system functions like a central heating system for the cluster, with the jets as the furnace and the cavities and sound waves as the radiators distributing the warmth. Without this input, the cluster's core would have long since collapsed into a starburst frenzy. Cosmological simulations now hinge on this very process to create realistic virtual universes. When scientists run models without including jet feedback, the results are catastrophic overcooling. The simulated central galaxies become far too bright and massive, forming stars at impossible rates. Only when the models include the heating from black hole jets do they reproduce the observed properties of real clusters, such as the precise relationship between a cluster's X-ray luminosity and its temperature. This agreement between simulation and observation is a powerful validation. It tells us that jet feedback is not a minor side effect. It is a fundamental pillar of galaxy cluster evolution, a regulatory force as essential as gravity itself. The supermassive black hole, through its jets, becomes the master of its domain, a quiet architect maintaining order on a scale of millions of light years. Even the most powerful cosmic beam cannot last forever. The journey of a relativistic jet is a constant battle against the subtle resistance of intergalactic space, a slow and steady fading over millions of years. This grand deceleration begins as the jet's leading edge, the hot spot, relentlessly pushes against the thin gas of the intergalactic medium. Each collision transfers a tiny amount of the jet's momentum to the surrounding material, a persistent drag that gradually slows the entire structure. Simultaneously, instabilities begin to creep in, like a garden hose stream that eventually begins to waver and break apart. The jet's perfect collimation can be disrupted. Kink instabilities can develop, warping the magnetic field lines that guide the jet and causing the beam to wobble and lose its tight focus. All the while, the jet is bleeding energy through the brilliant synchrotron radiation that allows us to see it, a continuous drain on its power reserves. Over time, these processes work in concert to slow, disrupt, and ultimately quiet the once ferocious outflow. We see the final stages of this life cycle in objects known as giant radio galaxies. Their colossal, often faint radio lobes stretch for millions of light years, but the bright, continuous jet connecting them to the central galaxy has vanished. These are the ghosts of past activity, the fading remnants of a jet that has long since shut down. The energy stored within these vast bubbles does not simply disappear. It slowly dissipates, contributing to the overall heat and turbulence of the intergalactic medium and enriching it with accelerated particles. This cyclical nature of jet activity is a fundamental aspect of galactic life. A black hole may erupt with a powerful jet for 10 million years, only to fall quiet for 100 million, its activity governed by the availability of fuel. A sudden influx of gas from a galactic merger can restart the engine, igniting a new jet that may inflate fresh lobes within the faded relics of its predecessor. How many such cycles has a typical galaxy undergone in its long history? The fading light of these cosmic jets tells a story of intermittent fury, a pulse of energy that shapes its surroundings long after the beam itself has vanished, leaving behind only a gentle warmth in the vast cosmic dark. The invisible architecture of the cosmos may subtly guide these colossal beams of energy. While dark matter refuses to interact with light, its immense gravitational presence forms the hidden skeleton upon which galaxies are built. This unseen mass, concentrated in vast halos around galaxies and clusters, could influence a jet's journey in profound but indirect ways. The primary interaction is gravitational. A dense, uneven distribution of dark matter could act as a cosmic lens, gently bending the path of the jet through the warping of space-time, a phenomenon known as gravitational lensing. This might cause slight distortions or even multiple images of the same jet if we were able to observe with enough precision. Furthermore, as a jet plows through the invisible halo, it could experience a subtle drag known as dynamical friction, a resistance caused by the gravitational wake the jet creates in the dark matter sea. This effect, while minuscule over short distances, might contribute to the gradual deceleration of a jet across its million-year lifespan. Some theoretical proposals venture into even more exotic territory, suggesting that under specific conditions, dark matter particles annihilating each other could produce standard particles and radiation, potentially adding a faint, additional glow to the jet's own emission. The challenge, however, is immense. Our current telescopes cannot directly distinguish this hypothetical dark matter signal from the jet's own brilliant light generated by synchrotron radiation and other processes. Experts in the field consistently caution that these ideas remain highly speculative. The observed properties of jets are explained remarkably well by the established physics of black holes and magnetic fields without needing to invoke dark matter interactions. Yet, this very difficulty makes the possibility so compelling for future research. The next generation of observatories, with their unprecedented sensitivity, may finally detect the faint gravitational imprint of a dark matter halo on a jet structure, or uncover a strange spectral signature that defies conventional explanation. This tentative connection reminds us that the universe is a web of interrelated forces, both seen and unseen. The stability and paths of these brilliant cosmic engines might ultimately be shaped not only by the violent physics at their core, but by the silent, gravitational hand of the dark universe itself. The sheer power of a cosmic jet can feel impossibly abstract, yet we encounter its fundamental principles in everyday life. Think of a simple garden hose. Water flows out in a wide, chaotic spray until you place your thumb over the opening, narrowing the stream into a fast, focused jet that can reach far across your lawn. This is collimation in action, a direct analogy for how magnetic fields and external pressure squeeze a black hole's chaotic energy into a narrow beam that crosses galaxies. The accretion disk itself behaves like a colossal whirlpool, where gas and dust spiral inward just as water circles a drain, gaining tremendous speed and energy before it plunges into the unseen depths. These comparisons are not perfect, of course. A whirlpool on Earth is governed by water pressure and gravity, while its cosmic counterpart operates under the bizarre rules of relativity, where gravity warps space-time itself. But they give us a crucial foothold, a way to grasp the mechanics of these distant engines. We can even picture the process of frame dragging, where a spinning black hole twists the fabric of space around it, by imagining a spinning top slowly twisting a tablecloth laid beneath it. The magnetic fields that channel the jet can be visualized as immensely strong rubber bands, wound up by the black hole's spin until they snap with energy, flinging particles outward. And the intense brightness of a blazar, a jet pointed right at us, is like a laser pointer beam aimed directly into your eyes, its light amplified and concentrated by its own incredible velocity toward you. What everyday object would you use to describe a jet's incredible stability over millions of years? These simple analogies do more than just explain. They connect us to the cosmos, transforming distant mathematical wonders into physical intuitions we can feel and understand. They remind us that the universe, for all its grandeur, often builds its most spectacular displays from principles we can find right here at home. The data on a galactic jet does not arrive as a brilliant image, but as a stream of numbers, a cryptic message requiring years of patience to decode. Behind every discovery is a researcher like Heino Falk, who spent decades nurturing the audacious idea of imaging a black hole's shadow before the Event Horizon Telescope collaboration made it a reality. His story is not one of instant success, but of persistent advocacy and international cooperation, convincing skeptical colleagues and funding agencies to support a project many thought was impossible. For every veteran theorist, there are countless graduate students spending late nights writing code to filter out atmospheric interference, their screens glowing in quiet observatory control rooms. They face the constant challenge of securing precious time on the world's most powerful telescopes, where a single night of observation might be granted only after a highly competitive proposal process. The triumph of a breakthrough is deeply personal. One astronomer described the moment a new algorithm finally cleaned up the data, revealing the magnetic field structure of a jet in stunning clarity, as a feeling of profound connection to the distant universe. These personal stories reveal that astrophysics is fueled by human curiosity and resilience. It is a field built on collaboration, where a postdoctoral researcher in Japan shares their analysis with a team in Chile, who then adjust their observation strategy in real time. This communal effort, spanning continents and careers, turns individual curiosity into collective understanding. The quest to map these cosmic engines is a human story, a testament to our enduring desire to look into the darkness and comprehend the magnificent forces at work. Science fiction has long painted these cosmic jets as both majestic gateways and terrifying hazards. In the film Contact, a fictionalized version of the quasar 3C273, serves as a cosmic transportation system, its jet engineered by an advanced civilization to carry a spacecraft across the universe. While the science of using a jet for travel remains firmly in the realm of imagination, the portrayal captures their immense power and scale with a surprising degree of visual accuracy. The movie Interstellar took a different approach, depicting the accretion disk and jets of the fictional black hole Gargantua with a scientific rigor guided by a Nobel Prize-winning physicist. The resulting visuals, a luminous disk of light wrapped around a dark sphere, brought the theoretical models of astrophysicists to life for millions of viewers, creating an iconic and largely truthful representation of these cosmic engines. These fictional depictions, while taking creative liberties, often get the fundamental premise right, that a supermassive black hole is the energetic heart of a system capable of launching focused beams of energy across interstellar space. Video games and literature have also explored these ideas, sometimes anticipating scientific discussions. Stories featuring wormholes or hyperdrives that resemble collimated jets explore concepts that researchers actively model, even if the technologies are pure fantasy. This cultural feedback loop is powerful, where a striking image from a film can inspire a young person to pursue astrophysics, their curiosity first ignited by a story. How many of today's astronomers first glimpsed the wonders of the cosmos not through a textbook, but on a movie screen? The role of science fiction is not to provide a perfect documentary, but to stretch our collective imagination, to make the truly alien feel tangible, and to frame scientific discovery as the greatest adventure of all. By translating complex equations into visual spectacles, these stories build a vital bridge, inviting the public to share in the awe and mystery that drives real scientific exploration. The cultural journey of the relativistic jet, from a theoretical oddity to a cinematic icon, demonstrates how our stories about the universe evolve in lockstep with our scientific understanding, each pushing the other toward new horizons. A new era of cosmic observation is dawning, driven by instruments of unprecedented power. The Square Kilometre Array, a vast network of radio antennas spanning continents, will act as a microscope for the universe. Its phenomenal sensitivity will map the faintest magnetic fields threading through jets, tracing their structure back to the very edge of the event horizon in galaxies millions of light-years away. We will watch these cosmic beams evolve in real time, observing knots of energy form and dissipate over mere decades instead of millennia. Simultaneously, the James Webb Space Telescope peers into the infrared, a domain perfect for piercing the cosmic dust that shrouds the earliest galaxies. It will find the most distant quasars, their infant jets caught in the act of formation just after the Big Bang, revealing how these engines first ignited and began shaping the primitive cosmos. This multi-wavelength assault continues with missions like the Advanced Telescope for High-Energy Astrophysics, Athena. From its orbital perch, Athena's powerful X-ray vision will precisely measure the temperature and motion of gas shocked and heated by jets, quantifying the immense energy they deposit into their surroundings. But perhaps the most revolutionary data will come from sensing the universe not by light, but by its vibrations. The Laser Interferometer Space Antenna, LISA, will open the low-frequency gravitational wave window, listening for the hum of merging supermassive black holes. By correlating these space-time ripples with the sudden flare of a newborn jet, we could witness the direct trigger of a cosmic engine, linking the collision of black holes directly to the launch of these brilliant outflows. Experts predict these tools will finally allow us to pinpoint the exact composition of jets, distinguishing between lightweight electron plasmas and heavier proton flows by detecting the elusive neutrinos they produce. We stand on the verge of moving from seeing these structures as distant, static sculptures to understanding them as dynamic, evolving systems. What new laws of physics will we uncover when we can finally watch a jet being born? The next decade promises not just answers, but a fundamental shift in our perception of these titanic forces. The mysteries of these cosmic jets are no longer reserved for scientists in remote observatories. You can join this exploration from your own home, becoming a citizen scientist with just a computer and an internet connection. Platforms like Zooniverse host projects where volunteers help classify thousands of real images of galaxies and their jets, data directly from the world's most powerful radio telescopes. Your own eyes can spot patterns and features that computer algorithms might miss, contributing directly to new discoveries. The Galaxy Zoo initiative is a perfect example, where public participation has led to the identification of unusual galaxies hosting powerful jets, findings that have been published in major scientific journals with the volunteers credited as co-authors. This is not a simulation, it is real data, and your curiosity can help write the next chapter in our understanding of the universe. For those who prefer to look up, even a modest backyard telescope can sometimes track the bright, variable flicker of a blazar, an active jet pointed right at Earth. Planetariums and science centers worldwide offer stunning visualizations that bring these distant engines to life, while open data archives from missions like the Hubble and Chandra space telescopes allow anyone to download and process the same images used by professional astronomers. Experts in public outreach encourage a mindset of lifelong learning and healthy skepticism, urging everyone to ask questions and seek evidence. This engagement fosters a society that is not only informed but also inspired. How might you find a moment to connect with these cosmic wonders in your own routine? Perhaps by joining an online star party, exploring a data set, or simply sharing a stunning image with a friend. Empowering public participation ensures that the awe of these galactic engines resonates with a global audience, transforming distant mysteries into a shared human experience. This profound knowledge of cosmic engines arrives at a cost, demanding immense resources and international cooperation. We invest billions in building telescopes and supercomputers not for a simple picture, but to answer fundamental questions about our place in the universe. This investment in pure science, in understanding the forces that shape galaxies, often yields unexpected rewards for society. The same advanced computing techniques developed to simulate a black hole's jet are now used to model complex plasma reactions, research that could one day lead to practical fusion energy here on Earth. The algorithms that clean up faint radio signals from distant quasars improve medical imaging and global communication networks. This is the hidden value of fundamental research, a rising tide that lifts all boats of human knowledge and capability. The global nature of this endeavor is itself a profound ethical statement. Projects like the Event Horizon Telescope require observatories across the globe to work in perfect harmony, from the mountains of Hawaii to the high deserts of Chile and the frozen plains of the South Pole. This collaboration transcends national borders and political differences, uniting humanity in a shared quest for understanding. It demonstrates that our greatest challenges, whether exploring the cosmos or addressing issues like climate change, are solved through collective effort and shared data. This spirit of open inquiry must be balanced with a deep responsibility. The search for intelligence beyond Earth, perhaps by analyzing anomalous patterns in a jet structure, carries a weighty ethical dimension. How would we handle such a discovery? The scientific consensus strongly advocates for careful, international consultation, prioritizing understanding over sensationalism. The goal is to foster a sense of wonder and connection, not fear. The true ethical core of this pursuit lies in its power to inspire. By sharing the story of these galactic engines, we ignite a passion for critical thinking and evidence-based reasoning in the next generation. We are not just building better telescopes, we are nurturing more curious and engaged citizens. The responsibility of cosmic knowledge is to ensure that this powerful light of discovery illuminates a path forward for all of humanity, guiding us toward a future built on wisdom, cooperation, and a profound respect for the universe we are only beginning to comprehend. The most violent events in the universe produce some of its most breathtaking art. When we see the iconic image of the jet streaming from Galaxy M87, we are not looking at a simple photograph. Those vibrant blues, radiant reds, and brilliant yellows are a carefully crafted translation, a false color palette assigned by scientists to represent different energies and physical processes. The deep crimson might trace the faint glow of synchrotron radiation from low-energy electrons, while the electric blue could map the fierce intensity of X-rays from hyper-accelerated particles. This visualization transforms raw data into a masterpiece, turning the physics of magnetic fields and shock waves into a visual symphony that our minds can appreciate. It is a bridge between cold, hard numbers and profound human emotion, allowing us to feel the grandeur of a structure we could never truly witness with our own eyes. The techniques behind these images are as sophisticated as the science they represent. Data from radio telescopes, X-ray observatories, and optical instruments are layered together, each wavelength of light assigned a hue from the visible spectrum. Astrophotographers and data renderers become cosmic artists, balancing scientific accuracy with aesthetic clarity to produce an image that is both informative and emotionally resonant. In this way, a jet structure becomes intuitively understandable, its knots and bends telling a story of past eruptions and ongoing collisions. The result often bears a striking resemblance to phenomena we know on Earth. The shimmering, curtain-like structure of a jet can recall the ethereal dance of an aurora, another natural display powered by charged particles spiraling along magnetic fields. The brilliant, forked filaments within a jet's lobes can echo the sudden, branching fury of a lightning strike, a shared pattern of energy finding the path of least resistance across a vast gap. These visual parallels connect the alien to the familiar, reminding us that the same fundamental forces are at work from our atmosphere to the intergalactic void. What is it about these cosmic structures that you find most beautiful? Is it their immense scale, their perfect symmetry, or the sheer power they represent, rendered in a silent, colorful ballet? This aesthetic appeal is not just a side effect, it is a powerful tool for education and inspiration. A single, beautiful image can ignite a lifelong passion for science, making the invisible forces of the cosmos tangible and stirring a sense of wonder that pure data alone cannot convey. The same elegant physics that carves paths between galaxies also sculpts the birth of new stars. Far from the chaotic cores of active galaxies, in the quiet nurseries where stars are born, we find protostellar jets. These slender beams of matter erupt from the poles of infant suns, punching through the surrounding cocoon of gas. The scale is vastly different, spanning mere light years instead of hundreds of thousands, yet the underlying engine is strikingly familiar. A young star gathers material from a spinning disk of gas and dust, and through a combination of magnetic fields and rotation, it focuses some of that inflowing matter into a pair of opposing jets. The process is a miniature version of the galactic engine, a scaled-down demonstration that the universe reuses its most effective designs. We observe these outflows in objects like Herbig-Haro 334, where the jet's collision with interstellar gas creates glowing knots of light, a small-scale echo of the hotspots in giant radio galaxies. Even the isolated corpses of dead stars can launch their own relentless beams. A pulsar, the ultra-dense, rapidly spinning remnant of a supernova, acts as a powerful cosmic lighthouse. Its intense magnetic field, trillions of times stronger than Earth's, rips charged particles from its surface and accelerates them along its poles, creating a dazzlingly focused jet. The Crab pulsar, the heart of a supernova witnessed 1,000 years ago, drives a jet that torques and changes visibly over years, not millennia. This offers a unique, fast-motion view of jet dynamics, showing how even without a massive accretion disk, pure spin and magnetism can generate a formidable outflow. The primary distinction lies in the power source. A pulsar jet is powered by the object's immense rotational energy, slowly bleeding its spin into the jet, much like the spin-powered jets from supermassive black holes. At the opposite extreme of the energy scale lie gamma-ray bursts, the most powerful explosions since the Big Bang. Lasting from mere seconds to a few minutes, these catastrophic events are thought to signal the birth of a new black hole during the collapse of a massive star or the merger of two neutron stars. In these fleeting moments, an ultra-relativistic jet is launched, and if one of those jets is pointed at Earth, we see the brilliant flash of a gamma-ray burst. The power concentrated into such a brief, narrow beam is almost incomprehensible, outshining entire galaxies for a few seconds. While the event is transient and violent compared to the steady output of an active galaxy, the jet launching mechanism shares the same core ingredients: a newborn black hole or neutron star, a swirling torus of debris, and wound-up magnetic fields providing the collimation. This comparative journey reveals a profound unity. From the stellar nurseries in our own galaxy to the most distant cataclysms, the same fundamental recipe creates a jet. Gravity provides the fuel, rotation gives it structure, and magnetism provides the nozzle. The incredible variation we see is simply a matter of scale and duration. A protostellar jet might be powered by an object 1,000,000 times less massive than a supermassive black hole, and a gamma-ray burst jet might last for a minute instead of millions of years, but the physical laws governing them are identical. This scalability is a powerful testament to the universality of physics, suggesting that once the universe discovered an efficient way to focus and expel energy, it employed it everywhere, from the smallest stellar births to the largest structures in the cosmos. How many other cosmic patterns hidden by scale or time share this same elegant commonality? These immense structures force us to confront the very nature of reality. A jet stretching across hundreds of thousands of light years is not merely an object. It is a dynamic argument written in energy, testing our fundamental ideas about space and time. The relativistic effects we observe, where time slows and motion appears to break cosmic speed limits, are not illusions. They are direct evidence that the universe operates by rules far stranger than our everyday intuition allows. Causality itself becomes fluid when information is carried by a beam moving at 99% of the speed of light. An event at the jet's base and a flicker at its distant tip are connected in a way that challenges our simple notions of cause and effect, revealing a cosmos woven together by the flexible fabric of spacetime. This profound connection suggests an underlying order, a set of mathematical principles that govern everything from the smallest particle to the largest cosmic structure. The sheer prevalence of these jets tells us something crucial about the universe's architecture. Their existence in so many galaxies confirms that supermassive black holes are not cosmic accidents, but standard features, integral components in the life cycle of galaxies. This points toward a universe where extreme physics is not the exception, but a common, even necessary part of cosmic evolution. Are these jets an inevitable outcome whenever gravity, rotation, and magnetism converge under the right conditions? The evidence from stellar nurseries to galactic cores suggests yes, that the universe has a preferred mechanism for focusing and expelling energy. This cosmic imperative toward structure, even in the most violent of circumstances, hints at a deep-seated order within the apparent chaos. This order has direct consequences for our own existence. The feedback from these jets regulates the growth of galaxies, preventing them from burning through their fuel too quickly. This process creates stable environments where stars can form at a measured pace, and planetary systems can persist for billions of years. It forces a profound philosophical question, one that cosmologists often ponder within the context of the anthropic principle. Could life have emerged in a universe without these galactic engines? Without the regulating influence of jets, galaxies might exhaust themselves in frantic starbursts, leaving no time for stable solar systems or the slow, patient evolution of life. The jets, in their immense power, become silent gardeners on a cosmic scale, carving out the conditions for potential habitability. They are not just wonders to observe, but active participants in creating a universe capable of asking questions about itself. To understand them is to grasp a fundamental thread in the tapestry of existence, one that connects the destiny of galaxies to the possibility of our own awareness. What does it mean that the same forces that power these terrifying beams also quietly nurture the cosmic conditions that allow us to be here, to look back and to wonder? These brilliant beams are far more than distant spectacles. They are fundamental architects of the cosmos, actively shaping the destiny of galaxies. Our journey has taken us from the silent trap of the supermassive black hole, through the violent whirlpool of its accretion disk, and into the focused power of twisted magnetic fields. We have watched these jets collide with intergalactic space, heating gas and regulating the birth of new stars, and we have glimpsed the future where new telescopes will witness their violent birth. The next time you look up at the night sky, remember that the darkness is not empty. It is alive with these colossal engines, driving the grand evolution of the universe across billions of years. Their story is a testament to the elegant, often violent, physics that connects the largest structures in existence to the very possibility of our own. We would love to hear what amazed you most. Share your thoughts and questions in the comments below, and subscribe to keep exploring the profound mysteries of space.